All right, so I want to if we can, quickly go over the any leftover questions you have on the chapter 13, multiple choice A, so you guys can do the B version tonight. So that's this one?
Yeah.
All right. So I thoroughly expect, and this is kind of like a thing, like if we're going to take the time to do this, I need you guys to be fully invested in this. All right. So if I look out and you're playing games or watching something on your computer, I may lose my mind. Do you understand? It is so obvious to us when you guys are doing something other than what we're doing here on your computer screens. Like, you're like, oh, they'll never know. They literally know every time. All right? You guys understand me? So you need to focus. All right? All right, here we go. An asteroid hits a golf ball of mass m on the moon where there's no atmosphere and the acceleration to gravity is g over 6. Oh, where g is the acceleration to gravity on Earth. No problem. Assume that the golf ball is in contact with the club for time t. Just after losing contact with the club, the ball has an initial speed of v directed at an angle of theta above the horizontal. What is the magnitude of the average force exerted on the club during contact? So this is a hard question because we segregate our questions or our units to topics. So like chapter 13, but this is not a chapter 13 question. Okay? In any way. So what it tells you is this. So you have a golf club. Okay. So here's your golf club here. Okay. And it hits the ball. And the ball leaves at an angle theta with speed v. It's a v or v0. That's two, right? Angle theta. Okay. Now the thing about this is that it says, what is the magnitude of the average force exerted on the club? Well, I mean, there's different contexts for force, correct? But this is the force of the club on the golf ball. So what do I know about force? If I think about it in terms of the force concept, force is equal to the mass times the acceleration. True? If I think about it in a momentum context, you know that force times the time is equal to the mass times the change in velocity. I think about it in an energy context, the work is equal to the force times the distance, which is equal to the change in the kinetic energy. So given these three contexts of force, which do you think is the appropriate to answer it here? Go ahead.
Could you use the force one on the left?
You could. So in order to know this force, you would have to get you'd have to know the mass and the acceleration. Do you know these two?
Well, you know the mass and you know the acceleration is just velocity over time.
So isn't that this one then?
Well, that's true.
Right? So, but what Anthony points out is the correct understanding is you would need two steps to do this one, but this is here. What he said was, if I take my idea that acceleration is the change in velocity divided by the change in time, if I know the change in velocity and the change in time and the mass, then I can get the force. But isn't that really just this equation here? Okay? So if I'm going to solve for force, I'm going to do this, right? Mass, change in velocity divided by the change in time. Now, one of the things that's interesting about this is because we're talking about the change in velocity, what was the initial velocity? It was 0. So the change is equal to the final. So anytime we talk about change, the change in velocity, for example, is the final velocity minus the initial velocity, right? And if the initial velocity is 0, then the change is equal to the final. So, you guys with me on that? So,